Now student, we are going to discuss question number 7.17. Clear? In this question it is given to you, keeping the source frequency equal to resonating frequency of series LCR circuit if the three element L, C and R are arranged in parallel, and then we have to show that the total current in parallel LCR circuit is minimum at this frequency, and we have to obtain the current RMS value in each branch of the circuit for L equal to 5 Henry, C equal to 80 microfarad and R equal to 40 ohm. Clear? And for the AC source of EMF 230 volt. This is 230 volt for this frequency. It is given to you. Clear? So let us try to understand this question. So concentrate on a screen. Clear? Now in this question it is given, we have three elements. Let's suppose we are saying, let's suppose this is L. Clear? This is inductor. I am saying this is capacitor. Clear? And let's suppose this is resistor. All are connected in parallel combination. Clear? And now it is connected with an AC source. Clear? And this AC source is having VRMS. It is given in a question. This is equal to 230 volt. Clear? It is given to you 230 volt. Clear everyone? Yes. Now in this question it is given to you, if the source frequency is equal to resonant frequency of series LCR circuit. Clear? So now we can see value of L, C and R. It is given to you in this question. R value we have 40 ohm. Clear? Value of C we have, this is 80 microfarad. Clear? And what about L? Inductance, it is given to you 5 Henry. Clear? Now we know whenever we are talking about series LCR circuit, so in series LCR circuit at resonance condition, you can see we always find XL, this should be equal to XC, means inductive reactance, this is equal to capacitive reactance. So inductive reactance, it is given by omega L, this should be equal to 1 upon omega C. Clear? So from here we can see this is given by omega square 1 upon LC. Clear? Omega square, this should be equal to 1 upon LC. Clear to everyone? Yes. So now we can see value of omega, this is given by under root of LC. Clear? Omega is given, this is equal to 1 upon under root of LC. Clear to everyone? Yes. So omega is equal to 1 upon under root of LC. Clear? Now this is actually known as resonant frequency. Clear? So from here you can say resonant frequency omega R. Clear? It is given by 1 upon under root of LC. L value is given to you 5 Henry. Clear? This is 5 Henry. And what about we can say C? What about C? C is given to you 80 into 10 to the power minus 6. Clear? So 5 into 80 into 10 to the power minus 6. So we can write like this, omega R, this should be equal to 10 to the power 3 divided by, now we can say 5 multiply 80. 5 multiply 80, this is equal to 400, and if you take square root we can say this is equal to 20. Clear? So now we can say this is given by 1000 divided by 20, and this is equal to 50 radian per second. Clear? This is equal to 50 radian per second. Clear to everyone? Yes. Now we can say this is value of resonant frequency. Clear? Now it is given in this question. Now we have to show if we connect all these elements in a parallel combination, that the total current that we found at this frequency, it is minimum. Yes or no? So how can we find? So for that one, first of all you have to keep one thing in mind. Whenever we have this alternating source in parallel to these elements, potential difference across each element, it remain same. Clear? And you know how can we write? Actually we can write like this. Let's suppose current, this is flowing through this source, this is IS. I can say in this direction current is flowing IR, this is IC, and we can say this is IL. Here you cannot write IS equal to IR plus IL plus IC. Why? Because now you can say in every component there is a phase difference between voltage is to be taking place. Clear? So now how can we write? We can write like this. Concentrate on the screen. Now let's suppose I am taking this direction as a direction of VR, and in this direction we will find this is IR. Clear? In the upward direction we have this is IL, clear, this is IL, and let's suppose I am saying this value we have, this is IC, clear, yes or no. So now let's suppose I am taking that IC is greater than IL, so in this case we can say this is equal to IC minus IL, this is IC minus IL, and I can say this is equal to IR, clear. Now what about resultant? I can say this resultant is given by in this direction, and this should be equal to, we can say this is equal to IS, clear. So we can actually write like this, IS, this should be equal to under root of, we can say IR square plus IC minus IL whole square, yes or no? Yes. So now we can say, we can write like this, let's suppose if we replace all these components by a single component, and you can say that impedance is given by capital Z, clear. So at that time we can say this is, we can say V is the RMS potential, or we can say RMS voltage of source. So we can say this is V divided by Z, this should be equal to under root of, we can say this is V square divided by, clear. Now we can say we have resistance capital R, so this is R square plus this is V minus, we can say this is XC minus V divided by this is XL whole square, clear to everyone. So now we can say if we take V common, we can write this is equal to 1 by Z, this is equal to under root of 1 upon R square plus I can say 1 upon XC minus 1 upon XL whole square, yes or no. Now you can say whenever we are talking about resonant frequency, at resonant frequency you can say XC equal to XL, yes or no. So when XC equal to XL, it means we can say this term becomes 0, yes or no. It means we can say 1 by Z value, this value we are getting, this is equal to only 1 upon R square, clear. So at resonant condition you are getting this term 0. If let's suppose you do not have any resonant condition, at the time definitely you have to add some term with 1 upon R square. It means you are getting minimum value of 1 by Z, yes or no. So actually whenever I am writing like this, I am saying this is minimum value of 1 by Z, and this should be equal to 1 by R, clear. It means I can say maximum value of Z we are getting at this position, that is equal to R, yes or no. In the parallel combination, you are getting maximum value of Z at this resonant frequency, clear. So definitely when we have maximum we can say impedance, at that time we can write, we will find this current minimum, clear, and this minimum current is given by V upon G Z max, clear, and we can say this is equal to R. So I can say this I minimum, it is given by V RMS divided by R, yes or no. So now we can say V RMS, in this question it is given V RMS is equal to 230 volt, so this is equal to 230 divided by, what about R? R value is given 40 ohm, so we can say this is 40, 0 and 0, this one is cancelled out, clear. So I can say this is equal to 5.75, clear. So we can say this is 5.75 ampere, clear. So we can say this is 520, we have 3, so we can say this is 6, 7, correct, and this is 5, clear. So this is I minimum, so I can say minimum current, clear, obtain the current RMS value. So I RMS in this all circuit, or we can say this is value of I, clear, this is value of IS, it is given by 5.75 ampere, clear. But in this question our objective is to find value of current in each component, clear. So we can write this IR is given by, this is V RMS divided by R, clear, this is equal to 230 divided by 40, you are getting same value 5.75 ampere, clear. Now can I find what is value of current in a inductor? Yes, we can write like this, value of IL, clear, value of IL, this is given by V RMS divided by XL, clear. Now what is value of VRMS? VRMS value we are getting, this is 230 divided by what is XL? XL we can say this is equal to omega L, yes or no. So this is equal to omega L, so 230 divided by value of omega you are getting, this is 50, Yes or no? You are getting this omega equal to 50, clear, and multiplied with, now value of L is given 5 Henry, so this is equal to 5. So 230 divided by 250, clear, this 0 and 0 is cancelled out, clear. So now if you solve it, you can find 0.9, clear, this is 225. Now we have only we can say this is 2 to 5, we have 5 left, so 0.92 ampere, clear. So this is current that is flowing in a inductor, clear to everyone. Now you can say, now we can find current this is flowing in a capacitor, clear. So now concentrate. Now we are going to discuss how can we find value of current that is flowing in a capacitor, clear. Now we can say value of IC, clear, value of IC, this is given by Vrms divided by, we can say this is XC, clear. So value of Vrms, this is equal to 230 divided by, now what is value of XC? XC is given by 1 upon omega C, clear. So now we can say this is 230 into omega value we have 50, and what about C? C value is given to you 80 microfarad, so 80 into 10 to the power minus 6, clear. So we can see 23 into 100 into 8 into 10 to the power minus 5, clear. So we can see this is 23 into 8, clear, multiply 10 to the power minus 3, clear. Now if you multiply, you can see this is 24, we have 2, and we can say 16, we can say 18, yes or no? Yes. Just a minute. So from here you can see in the calculation 230 multiply 50 into 80 into 10 to the power minus 6, clear. So we can write like this, 23 into 5 into 8 into 10 to the power minus 3, clear. So I can see this is 23 into 40 into 10 to the power minus 3, clear. So now I can write this is equal to 12, we have 1, so 92 into 10 to the power minus 2 ampere, or we can say this is 0.92 ampere, clear to everyone. Now you can say current flowing in a inductor and current flowing in a capacitor is same, clear, and we are also getting value of net current, 5.75, this is same as current that is flowing in a resistor, clear. It means we can say we cannot apply IS equal to IR plus IL plus IC, yes or no? Or now you can say, sir, when all the current is going through resistor, then why, from where we are getting this current? Actually current is flowing in every component, but actually potential that is produced in an inductor and we can say capacitor, they are out of a phase, or we can say they are lying at 180 degree to each other. So actually the net voltage cancel to each other, clear. So now we can say this is all about this question, clear to everyone. So student, we are going to discuss this question number 7.18, clear. In this question it is given to you a circuit containing a 80 millihenry inductor and a 60 microfarad capacitor in series is connected to a 230 volt 50 hertz supply. The resistance of a circuit is negligible, clear. So first I am drawing this circuit diagram. So let's suppose this is an inductor, clear, and it is connected with a capacitor. So we can say this is capacitor, clear, and it is connected with the AC source, and all values are given to you, clear. So value of L, this is equal to 80 millihenry, clear, this is 80 millihenry. And what about capacitance? Capacitance value is given 60 microfarad, clear to you? Yes. So now it is connected with our 230 volt and 50 hertz supply. So we can say this is 230 volt, and we have we can say Vrms is 230 volt and frequency is 50 hertz, clear. Now resistance of this circuit is negligible, means value of resistance is 0. We have to take 0. Obtain the current amplitude and RMS value, clear. So first of all we have to find current amplitude. Current amplitude means maximum value of current, clear, and we have to find RMS value, means IRMS, clear. So for IRMS first of all, if I write for number A, IRMS is actually given by VRMS divided by, we can say this is impedance capital Z. Clear? Now impedance is given by, now we can say this is equal to VRMS divided by, what about capital Z? Capital Z means we can say this is equal to, you can write like this is XL minus XC. Why I am writing like this? Because we can say this is impedance, and we can say reactance, inductive reactance, and we can say inductive capacitance, capacitive reactance. Inductive reactance and capacitive reactance both are in opposite phase. That's why I am writing this is XL minus XC. Clear? So value of VRMS, it is given to you 230 divided by, what about XL and XC? We can say this is equal to omega L minus 1 upon omega C. Clear? So we can say 230 divided by omega L minus 1 upon omega C. Clear? So now I can say IRMS. Clear? IRMS, and this is given by 230 divided by, now what is value of omega? Omega value we have no, this is given to you frequency, that is F. Clear? So we can write omega, this is equal to 2 pi multiply 50 multiply, what about value of L? L is given to you 80 millihenry, so this is 80 into 10 to the power minus 3. Clear? So we can say this is equal to XL. Now we are writing value of XC, so this is equal to minus XC. XC means we can say 1 upon omega C. Omega is given to you 2 pi into 50. Clear? This is omega. And what about C? Now we can say value of C, it is 60 microfarad. Clear? So we can say 60 into 10 to the power minus 6. Clear to everyone? So now we can say this is value of IRMS that we are getting. So now just we have to solve it. So we can write like this, this is 230 divided by, now if you solve it, you can say this is 2 pi multiply, we can say 40 into 10 to the power minus 1. Clear? 8 multiply 5, we have 40, and we can say this is 10 to the power minus 1 minus 1 upon, we can say this is 2 pi multiply 50 multiply 60. So we can say this is 3000 multiply 10 to the power minus 6. Clear? So now I can say this should be equal to 230 divided by. Clear? Now if you solve it, you can say this is equal to 8 pi minus 1 upon, we can say this is 6 pi into 10 to the power minus 3. Clear to everyone? So you can also write like this, this is equal to 230 divided by 8 pi. 8 pi means we can say this is 8 into 3.14. Clear? So near about you will get this value 25.13 minus 1 upon 6 pi, or you can say 1000 upon 6 pi. 1000 upon 6 pi you will get this is 53.05 near about. Clear? Now if you solve it, clear, if you solve it you will find 230 divided by something. Clear? So we can say this is equal to 230 divided by, now I can say this is 2. Clear? And 9 minus 1, this is 8. Clear? This is 2. I can say this is 7. Now we have 4 and this is 27.82. Clear? So if you divide, definitely you will find value of current in terms of RMS. Clear? So this value you will get near about 8.24 ampere. Clear to everyone? Yes or no? Yes. So this is all about IRMS. But what is our objective in this question? Our objective in this question is to find value of current amplitude and RMS. RMS we have calculated. Now we are going to find I naught. I naught is given by IRMS multiply under root of 2. Clear? Value of IRMS, you are getting this is 8.24. So 8.24 multiply under root of 2. Clear? So now we can say this is given by 8.24 multiply 1.414. Clear? So now I can say this is equal to we can say if you solve it you will find this value near about 11.7 ampere. Clear? So I can say this is maximum, or we can say this is peak value of current. Clear everyone? Now we are going to discuss part number B. Obtain the RMS value of potential drop across each element. Clear? So now we can find easily, we can write like this, just a minute, we can say, now I can say VRMS across inductor, it is given by IRMS into XL. Clear? IRMS we have this is 8.24, clear. IRMS we have this is 8.24. So 8.24 and multiply. Now Excel value you know, yes, this is value, this is related to Excel, so this is 25.13, clear. So definitely you can say 8 multiply 25, this is near about 200. So if you solve it, you will get this value near about 207 volt, clear. And now if I am talking about VRMS across capacitor, we can say this is given by IRMS multiply XC, clear. IRMS value we have this is 8.24, and what about XC? XC value we are getting 53.05, 53.05, clear. We are getting this value 53.05. So now if you multiply directly, you can say 50 multiply 8, this is near about 400, and we can say this value will come out to be more than 400, and if you solve it, you will say this will be come out to be 437 volt, clear. So now we can say this is all about part number B. Number C, what is the average power transfer to inductor? Now listen carefully. Actually we know one formula, P average. P average is given by this is VRMS, IRMS, and we can say this is cos of phi. Now we can say what is phase difference between voltage across inductor and IRMS. So definitely we know this is phase difference. Voltage leads with current by an angle pi by 2 in the case of inductor. So I can say in the case of inductor, you will find average power, this is 0, clear. Now if we are talking about part number D, what is average power transfer to capacitor, clear. So we can say average power transfer to capacitor, this is also 0. Why? Again you can say in this situation voltage is lagging behind with current by an angle pi by 2, clear. So this is again we can say average power is 0. Now number E, what is the total average power absorbed by the circuit? Now we can say the power, this is absorbed by this inductor and this capacitor, both are individually 0. So total power absorbed in a circuit, I can say this is equal to 0 watt, clear. So this is all about this question, clear to everyone. Now student, we are going to discuss this question number 7.19, clear. In this question it is given, suppose the circuit in exercise 7.18 has a resistance of 15 ohm, then what is obtain the average power transfer to each element of a circuit and the total power absorbed, clear. Now you can say let's suppose if I draw this circuit diagram, I can say this is inductor, let's suppose this is capacitor. Now we are connecting our resistance also in with a AC source, clear. Now value of resistance, it is given to you, this is 15 ohm, clear. What about value of C? Value of C we are getting 60 microfarad and 80 millihenry, clear. Yes or no? This is 80 millihenry and 60 microfarad. So 80 millihenry and this one is 60 microfarad, clear. And what about voltage source? 230 volt and 50 hertz, clear. So 230 volt comma we can say this is 50 hertz, clear. Now what is our objective in this question? We have to obtain average power, clear. It means first of all we will find impedance of this circuit, clear. Impedance is given by Z equal to, I can say now this is R square plus XL minus XC whole square, clear. Now you can say, you can also write it like this, this is 15 square plus, what about XL and XC? We can say this is given by 2 pi, because this is equal to omega L, omega is given by 2 pi f, so this is 2 pi f. And what about L? L is given to you 80 millihenry, so 80 into 10 to the power minus 3, clear. And what about XC? We can say XC equal to 1 upon omega C, clear. This is equal to 1 upon 2 pi, clear. What is value of F? F value is given to you, we can say this is 50, clear. And what about C? What is value of capacitance? This is given 60 into 10 to the power minus 6, clear. Now let us try to understand this calculation you have already done, yes, in the previous question. So we can write like this, value of capital Z, it is given by value of R we have, this is 225 plus, clear, 225 plus. Now we can say this value is equal to we can say this is 25.13 and this is 53.05. So we are getting this is 27.82. Clear? So directly I am saying 27.82, this is whole square. Yes or no? So from here you can write like this. This is equal to 225 plus, what about 27.82 square? 27.82 square, this is given by we can say 779.5. Near about this value you will get. Clear? So if you add it, clear, if you add it, you can say this is 200 and 700, this is near about 900. 25 plus 79, this 100 more, it means 1000. So 1000 plus value you are getting, and this value you are getting, this is 1004.5. Clear? Now if you take square root, clear, square root of this one, it is given by, we can say 31 point and we can say this is 7. Clear? Ohm. So this is the impedance of this circuit. Yes or no? So can we find value of IRMS? Yes, we can write like this. IRMS is given by, we can say this is V divided by capital Z. What about V? V is given to you, this is 230, and what about capital Z? Capital Z is given, this is equal to 31.7. Clear? 31.7. So now we can say if you calculate it, you will find this value near about 7.25 ampere, and definitely this current is less than compared to previous one. Why? Because we are also adding the impedance due to resistance. Clear? You are getting an additional term of 225, or we can say resistance. Clear? So now you can say our objective in this question is to find average power transfer. Again, you can say if we talk about Vrms and corresponding to L, we can say this is equal to what? We can say, because you can say this is equal to IRMS and multiply XL. Yes or no? So from here you can say we can write value of IRMS and XL. Yes, you can calculate it, but our objective is to find average power. So directly I am going for power. So what is average power across inductor? This is given by Vrms across L. We can say this is IRMS, and we can say this is cos phi. So in the case of an inductor, again you will find phase difference between RMS voltage and IRMS, and in this situation whenever you have a pure inductive case, pure inductive circuit, so in the case of pure inductive circuit, you always find voltage is leading with current by angle pi by 2. Clear? So now we can say this power, average power you are getting, this is 0 watt. Clear to everyone? Now how can we write average power and corresponding to, we can say, capacitance? This is again you will find like this: Vrms C IRMS, and we can say this is cos phi. Again you can say phase difference between potential difference, phase difference between potential difference and current, this is given to you 90 degree. Clear? So again we can say this average power we are getting, this is equal to 0 watt. Clear to everyone? This is 0 watt. So now we can say, can we find average power corresponding to resistance? Yes. Now it is given by IRMS square multiplied with R. Clear? So what is value of IRMS? IRMS value is given to you 7.25 ampere. Clear? So this is 7.25 whole square. What about multiply with R? R value is given to you 15 ohm. Clear? This is 15. Clear? So now if you solve it, you can say 7 multiply 7, this is 49, and 49 point something you will get, and you have to multiply it with 15. Clear? So this value you will get near about, I am directly telling you this answer, 789.5. Clear? So 789.5 watt you are getting this power. Clear? So this is average power of this resistor. Now if I talk about what is average power of this circuit, definitely average power corresponding to inductor and capacitor, this is 0. So I can say average power of this circuit, it is also given by, we can say this is corresponding to this circuit, it is given by 789.5 watt. Clear to everyone? So this is all about this question. So now student, we are going to discuss question number 7.20. Clear? In this question it is given to you a LCR series circuit with L equal to 0.12 Henry, C equal to 480 nanofarad and R equal to 23 ohm is connected to a 230 volt variable frequency supply. As you can see in this screen, actually I drew here already. This is series LCR circuit. We have three components: inductor, capacitor and resistor, and it is connected to a variable source, and we can say that is having VRMS 230 volt and standard. You can say you can find frequency also. Clear? So now in this question it is given number A part, what is the source frequency for which current amplitude will be maximum, and obtain the maximum value of current. Clear? Now we know when we find value of current is maximum. Clear? So if I write expression of current, we can say current, this is given by V by Z. Z we can say this is impedance of this circuit. Clear? So now we can say, if we are saying this is VRMS, this is also VRMS. Now important part, this current that is flowing, it is maximum when we can say this Z will be minimum. Clear? Now expression of Z, it is given by under root of R square plus we can say XL minus XC whole square. So this Z will be minimum when this term XL minus XC, this should be equal to 0. Clear? And this is possible only whenever we find condition of resonance. Clear? It means now we have to find source frequency. So directly you can say you will find we can say resonant frequency, and you know formula, it is given by 1 upon under root of LC. Clear to everyone? 1 upon under root of LC. So now I am writing omega R, this is equal to 1 upon under root of LC and 1 upon under root of, now what is value of L? L value is given to you 0.12 Henry. So this is 0.12 Henry and multiplied with C. Clear? Value of C is given 480 nanofarad. Clear? So I can say this is 480 into 10 to the power minus 9 farad. Clear? So now if you calculate, you can write like this: omega R, this should be equal to we can say 1 upon under root of 12 divided by 100 into 480, and we can say this is 10 to the power minus 9. Clear? I can say this one and this one cancelled out, and we can write like this: this is 10 to the power minus 1 and minus 9, and this is 10 to the power minus 1. So it becomes 10 to the power minus 10, and we can say this is equal to 10 to the power 5 divided by under root of 12 into 48. Clear to everyone? So now if you write omega R, this should be equal to 10 to the power 5 divided by, now if you multiply it, we can say 12 multiplied 48. Clear? So you can write like this: 12 multiply 50 minus 2. Clear? So now we can say this is 600 minus 24. So 10 to the power 5 divided by 600 minus 24, and we are taking square root. Clear? So from here you can say this should be equal to 10 to the power 5 under root of 576. Clear? This should be equal to 576. Clear everyone? So this is value of omega R we are getting, and we can say this is given by radian per second. Clear? Now so if you solve it, near about you will find this value 625 we have, that is 25, and 576 we have 24. Clear? So we can see omega R, this is given by 10 to the power 5 divided by 24. Clear? So if you solve it, you will find this answer near about, we can say 4176 radian per second. Clear to everyone? So this is, we can say this is resonant frequency. Clear? This is value of resonant frequency. But what is our objective? Our objective in this question is to find maximum value of current. For that one, first I will find IRMS. Clear? Or you can directly write like this: if we want to find maximum value of current, we can say this is given by V0 divided by Z. Clear? Maximum value of voltage, or we can say peak voltage, it is given by under root 2 times of VRMS. Clear? And it is divided by Z. In resonance condition, you always find capital Z is equal to capital R. Clear? So I can say this is divided with resistance. Value of resistance is given, yes, this is 23 ohm. So I can say this is 23. Clear? So from here we can see I0, this should be given by under root 2 divided by 23 multiply. What about VRMS? Clear? So VRMS, we can say VRMS, it is given by V0 and multiply under root of 2. clear. So now we can say, we can write like this, V naught multiply 2 divide by this is 23, clear. What is value of V naught? Value of V naught we have, this is we can say, actually this is what Vrms equal to V naught into root 2, clear. So V naught into, we can say 2 divided by 23, clear. So can we find value of, actually you know this is Vrms, yes. So directly actually we can write like this, listen very carefully. Directly we can write like this, I naught is given by under root 2 times of Vrms upon 23, yes. So now we can say this is under root 2 multiply Vrms, clear. Vrms we have, this is 230 volt, so this is 230 volt and this is divided by 23, I can say this is 10 under root of 2, clear. And this value we know, this is 10 into 1.414 and this should be equal to 14.1 ampere, clear. 14.1 ampere. So we can say this is maximum value or peak value of current we have, clear. So this is all about part number A, clear to everyone. So this is all about part number A. Now second part is given what is source frequency for which average power absorbed by the current is maximum, clear. So average power will be maximum when the current flowing in the circuit is maximum. Current will be maximum only whenever we have a resonance condition, clear. Resonance condition means we can say omega r, this should be equal to 1 upon under root of LC, clear. So directly you can say, we can write like this, if we talk about part number B. So in part number B we can say average power, but this is maximum power, clear. And we can say this is given by Irms square and multiplied with R, clear. So now we can say Irms we can write like this, this is I naught divided by under root 2 whole square multiplied with R, clear. So I can say this is given by I naught square divided by 2 multiplied with R, clear to everyone. So now we can say average power we can say it is given by I naught square. I naught value we have, this is 14.1 or you can say 10 root 2, yes. So directly you can say 10 under root 2 whole square divided by 2 and multiplied with 23, because resistance value we have 23 ohm, clear. So from here you can say this is 100 multiply 2 divided by 2 into 23, we can say 2 and 2, this one is cancelled out, clear. And this is given by 2300 watt, clear. So I can say this is maximum power, this is maximum power, we can say this is maximum power obtained, clear. And this value we are getting 2300. Now we have to actually also write what is the source frequency for which average power is maximum, clear. So maximum we can say source frequency at which the average power will be maximum, so that is equal to, we can say, resonant frequency, clear. And resonant frequency value you know very well, yes. We can say that resonant frequency is given by directly you can say omega r, this is 4167 radian per second, clear to everyone. So this is all about part number B. Now we are going to discuss for part number C. In part number C it is given to you for which frequency of source is the power transferred to the circuit half the power at resonant frequency, okay, and what is the current amplitude at those frequency, clear. Now let us try to understand. Actually what is our question, concentrate here. For which frequency of source is the power transferred to the circuit is half of the power at resonant frequency, clear. So I think you should have one thing in mind, that is given by omega. We can say this is given by omega r plus minus delta omega, clear. We can also write this equation, this expression we find whenever we are getting power at half of the power that we are getting at resonant frequency, clear. It means we can also write like this, this is f, we can say this is 2 pi, just a minute. How can we write omega, clear. Actually you can also write like this, omega, this should be given by omega r plus minus, clear, plus minus, and we can say this is equal to r divided by 2l, clear, yes. So now from here you can say, actually we know omega, it should be equal to 2 pi f, clear? So how can we write value of f? We can write like this. If we divide by omega 2 pi both sides, we can also write like this. Yes or no? Clear to everyone? Now we can say from here you can find this frequency in terms of f, or we can say hertz. Clear? We can say this is fr plus minus this is equal to r by 2l and this is 2 pi. Clear? Now actually you can also write it like this, f equal to fr plus minus. Now you can put all values. Value of r we have 23, divide by 2, multiply. What about l? Clear? What about l? L is given to 0.12, so this is 0.12 multiply 2 multiply pi. Clear? Pi value is given to you, you can say this is 22 by 7. Clear? So now we can say you can write like this, fr plus minus. Now you have to calculate this expression. Clear? So if you calculate it, clear, approximation you can take 23 and 22 near about, this is cancelled out, 7 is going in upward direction. Clear? 2 to 4, here we have this is 0.48, so 7 divided by 0.48 means we can say 70 by 4. Clear? 70 by 4 it will be near about. So I am directly telling you what expression you will get. You will get this expression near about 15.25. Clear? Clear to you? Yes. So or you can say nearly you can take this value is equal to 15 hertz. Clear? Now what is value of fr? Clear? Actually we know omega r, it is given by this expression. Clear? Omega r is given by 4167 radian per second. Clear? So 4167 radian per second, we can also write it like this. This should be equal to 2 pi multiply fr. Yes or no? So from here you can say fr, this is given by 4167 divided by 2 pi. Clear? 4167 divided by 2 pi. So now I can say this is 2, 0, 8, we can say this is 3, we have 1, so this is 5 divided by, I can say this is pi. Clear? So fr value is given 2083.5 divided by 3.14. Clear? So now if you solve it, you will find this value is near about, we can say 663 hertz, near about. Clear? So from here you can say what frequency range you are getting. We can say f is given by fr plus minus, we can say this is 15. Clear? So you are getting this value 663 plus minus 15. Clear? So two frequency at which you can say power is half of the maximum. Power is half of the maximum. It is given by, we can say this is 876. So we can say this is 678 hertz, or we can also write it like this, 663 minus 15. Clear? So this is equal to, we can say this is 8 and we can say this is 4, and this value we have in hertz. Clear everyone? So like this we can find value of f1 and f2. Clear to you? Clear? Yes. Now at this situation one more thing is asking to you in this question. Yes, frequency we have already find it. What is the circuit amplitude at this frequency? Clear? I mean sorry, which is the current amplitude? Clear? Current amplitude we actually we have to calculate current amplitude. Current amplitude is actually we can say it is given by IRMS divided by 2. Clear? Just current amplitude. Actually you can find this current amplitude like this. We know at this frequency power is half of the maximum. Clear? And we know power is given by I square r. So directly we can say power is directly proportional to I square. It means we can say whatever I naught that is we are getting. Clear? Or that we are getting, it is equal to under root of p. Yes or no? Clear? So from here you can say actually we are getting here I naught, this is equal to you can say this is p naught by 2. Clear? So from here you can say I naught, this is given by I naught by root 2. Clear to you? Again I am explaining what I write here. Clear? Actually we know p is directly proportional to I square. Clear? Or it means we can say when we have power half of the maximum power, so at the same time the current will be I can say current will be 1 by root 2 times of maximum current. Clear? So directly you can say I is given by this is equal to I naught by root 2. Clear? Clear to everyone? We can see why I am writing like this, because you know I square directly proportional to P. Now if we are doing half of the P, clear, at the time you can say current becomes 1 by root 2 times. That's why I am saying the maximum current becomes 1 by root 2 times of I naught. Clear? So from here you can see value of I naught. Value of I naught you know. Yes, value of I naught we know. This is given by 14.1, or you can say 10 root 2. Clear? So directly we can say 10 root 2. So 10 under root 2 divide by under root 2. We can say this value we are getting. This is 10 ampere. Clear to you? So at 10 ampere we can say we are getting power half of maximum power that we are getting at resonant frequency. Clear? Okay. Now we have one more part of this question. This is part number D. What is the Q factor of the given circuit? Clear? So actually Q factor always provides to you sharpness of the circuit. Clear? Or we can say if you are drawing a graph, how sharp that curve is. Clear? So it is given by Q factor. So directly you can say Q factor, it is given by one formula, omega r L divided by R. Omega r L divided by R. Omega r value we know, this is equal to we can say 4167 multiply what is value of L. Value of L we are getting, this is 0.12 Henry. Clear? So 0.12 Henry divided by, now we can say this is 23. Clear? So from here you can say if we remove this decimal, we can write this is 100, this is near about 2. Clear? This is near about 2. So we are getting this value to, we can say 0.83.5 and divide by 100. Clear? So this value of Q factor, this value of Q factor near about we are getting, this is 21. Clear? So this is all value of Q factor. Clear? So this is all about this question. Now student, we are going to discuss question number 7.21, and in this question it is given to you, obtain the resonant frequency and Q factor of a series LCR circuit with L equal to 3 Henry and C equal to 27 microfarad and R is given to you 7.4 ohm. It is desired to improve the sharpness of the resonance of the circuit by reducing its full width at the half of the maximum. Find by a factor of 2. Suggest a suitable way. Now let us try to understand. In this question it is given, we have a series LCR circuit. We can say this is L, this is capacitor C, and we can say this is resistor. Clear? Values is also given to you. L value we have, this is 3 Henry. Clear? Value of capacitance, this is equal to 27 microfarad. Clear? And value of R, it is given to you 7.4 ohm. Clear? It is also given. So it is desired. So let's suppose it is connected with an AC source. Clear? Now our objective first in this question is to calculate value of Q factor. Clear? So for that one, actually we know this formula, this is given by omega r L by R. Clear? How can we calculate omega r? Omega r is a frequency at a resonant condition. So we can say omega r, this is given by 1 upon under root of LC. Clear? So if I write values of L and C, I can say value of L, this is equal to 3 Henry, and what about capacitance? Capacitance value is given by 27 into 10 to the power minus 6. Clear? So from here we can write like this, this should be equal to 10 to the power 3 divided by under root of 3 into 27. Clear? So from here you can write like this, omega r, this is given by 1000 divided by, now we can say we can write this 27, 9 multiply 3, so this is equal to 3 multiply 3. So from here you can say we are getting this is 1000 divided by 9. Clear? And near about this value we are getting 111.11. So near about I am taking this is 111. Clear to you? So this is all about omega r. So if I put all this value of omega r, clear, because our objective is to find resonant frequency, we have calculated, and Q factor. So if I put this value 111 multiply, what about value of L? Value of L we have 3 Henry and divided by what is resistance R? Resistance R is given by 7.4. Clear? So from here we can write like this, this is equal to 333 divided by 7.4. Clear? So if you divide it, you can see near about, you can say 7 multiply 5, we have 35, 7 multiply 4, this is 28. So near about 28.5 you will get, yes or no? 7 4, just a minute, omega r L by A, clear? Omega r L by R, clear? Value of r is given 7.4, clear? So this value you are getting, this is 7, so we can say 7 4, yes 7 4, we can say 28. So near about we are getting this value 45, clear? So near about we are getting this value, clear? So this is we can say all about omega r, that is resonant frequency, and we can say it is all about Q factor, clear? Now we have one more question. It is desired to improve the sharpness of a resonance of the circuit by reducing its full width at half of the maximum, okay, by a factor of 2. So let's suppose if we want to decrease the value of if we want to increase, actually if we want to decrease value of width, actually you know this graph, actually if you draw this graph you will find this graph will be like this. Let's suppose we have these 2 points, and if we want to decrease this width by half, it means we have to increase sharpness by a factor 2, clear? Now let's suppose if we are keeping this omega r constant, if I am keeping this omega r constant, for omega r constant L should be constant, the value of L should not vary. It means if we want to increase value of Q, I have to reduce value of resistance, clear? So if I want to increase this Q factor by a multiple of 2, at that time we have to reduce value of resistance by a factor 2, clear? So I can say, I am suggesting to you, if instead of 7.4 ohm, if you are utilizing 3.7 ohm resistor, at that time you can improve this Q factor of this circuit, clear to you? So this is all about this question. So student, now we are going to discuss this question number 7.22, clear? And in this question it is given to you, in this question it is given to you, we have some part from A, B, C, D and E, clear? And we have to answer the following questions, clear? So concentrate. If we talk about first part number A, in this part it is given to you, in any AC circuit, is the applied instantaneous voltage equal to algebraic sum of instantaneous voltage across the series element of this circuit, clear? So is the same true for RMS voltage. Now concentrate. Let's suppose we have, this is inductor, let's suppose we have capacitor, and I can say this is resistor, and all are connected with an AC source like this, clear? I can say this is V, and we can say this is corresponding to L, this is C, and this one is R, clear? So I can say, let's suppose I am saying this is V naught sine of omega t, this voltage is varying in nature, clear to you? So now we can say in any AC circuit, we have this AC circuit, so is the applied instantaneous voltage equal to algebraic sum of instantaneous voltage across the series element of the circuit. So definitely you can see, whenever we are talking about instantaneous voltage, so instantaneous voltage definitely it will be distributed in L, C and R, clear? And at the particular time, the value of V, it should be equal to sum of this one and this one, means sum of potential across L, potential across C and potential across R, clear? So definitely I can say this statement is correct. But is the same true for RMS voltage? No, clear? You cannot write like this, V RMS is equal to RMS voltage across L, RMS voltage across C and RMS voltage across R, and we are doing the addition, clear? You cannot write like this. Why? Because there is a we can say there is an opposite phase between capacitor and inductor voltage, clear? So at the time actually you have to find resultant voltage, clear? And at the time you can say R and the resultant of VL and VC, they are perpendicular to each other, so directly you cannot say that V equal to VL plus VC plus VR, clear? So we cannot say for RMS voltage. Yes, for instantaneous voltage this statement is correct, clear? Now if I am going to discuss part number B, a capacitor is used in the primary circuit of an induction coil. Yes, why? Let's suppose if I am saying to you situation, a primary coil breaks, clear? A primary coil breaks, at that time you can say initially let's suppose a steady current is flowing in that primary coil, and finally it comes to 0 after a certain interval of time, it means value of current decreases. When value of current decreases, it means definitely induced EMF will be generated, because there is a change in the flux is to be taking place. Yes or no? So induced EMF will be generated, and if we connect a capacitor with the primary circuit of induction coil, at that time due to that induced EMF, that capacitor is charged, and we can say instantaneous sparking that takes place due to breaking of that coil, that is prevented. Clear? That's why we are using capacitor in the primary circuit of induction coil. Clear? Now we are going to discuss part number C. In this part number C, it is given an applied voltage signal consists of a superposition of DC voltage and AC voltage of high frequency. Okay. The circuit contains an inductor and a capacitor in series, show that the DC signal will appear across C and AC signal across we can say that is L. Now let us try to understand. Let's suppose we have this is L, and let's suppose this is capacitor, both are connected in a series. We have here this is voltage source. Clear? Initially I am taking this voltage source is to be AC voltage source, so I am saying this is VRMS. Initially we have AC voltage source, so at the time I can see voltage that is produced across this inductor, and voltage this is produced across this capacitor, this is VC. Clear? So I can write like this: value of VL, this is given by I times of XL. Clear? And we can say it is given by I times of omega L. Clear? Omega L. Now you can also write like this: I, we can say this is 2 pi f L. Now listen very carefully. Whenever we are talking about AC current, so for AC current we have a definite frequency. Clear? It means definitely we will find some value of voltage across this inductor. So this is value 2 pi FL. Clear? But if I am talking about this capacitor, clear? If we are talking about capacitor, we can say this is given by I times of XC. Clear? XC is given by this is 1 by omega C. Clear? I can say I, this is equal to 1 upon 2 pi FC. Yes or no? So from here you can say, if we have a certain value of BC, definitely we are getting here voltage across capacitor also. Clear? So what is this question? Question is given, an applied voltage signal consists of a superposition of a DC voltage and AC voltage. Okay. Then circuit consists of an inductor and capacitor. What will happen? Listen carefully. Now you can say this source it actually consists of DC plus AC. Now we talk about AC. Clear? In AC we can say all the potential difference you will find that is across the L as well as across C. Clear? But what about DC current? Clear? What about DC current? In DC current you can say we have frequency 0. So whenever we have frequency 0, the resistance that is offered by inductor, we can say this is equal to 0. Yes or no? I can say this is 0, and we can say resistance this is offered by capacitor, this is infinite, because value of frequency we have 0. Clear? So from here you can say this is infinity. It means I can say all the potential difference in the case of DC you always find across this capacitor only. Clear? And there is no potential drop across this inductor. That's why you can see in current electricity chapter, if you are connecting this coil into circuit, there is no effect in the resistance or there is no effect in the heating. Why? Because I can say the resistance offered by this coil, by this inductor with respect to DC current, that is 0. Yes or no? So I can say there is no use. You can assume it just like a single wire or a wire that is having 0 resistance. Clear? So I can say in the case of DC, all the potential drop you will find across this capacitor. But what about AC? In the case of AC, you will find some potential difference across this VL and some potential difference across this VC. Clear? And what is net potential? It depends on the magnitude of VL and VC. Clear? So this is all about part number C. Yes. Now, if we talk about part number D, in part number D, it is given to you a choke coil in series. A choke coil in series with a lamp is connected to a DC line. Okay. So a choke coil is connected in series with a lamp in DC line. Okay. The lamp is seen to be shine brightly. Fine. Insertion of an iron core in the choke causes no change in the length. Yes, because if we are talking about DC current, for the DC current resistance offered by choke coil is 0. So at the time, if you have a choke coil, you are inserting any we can say iron core, that causes there is no change in the brightness of a lamp. But what will happen when we are talking about there is an input of an AC line, AC current? So whenever we have input of AC current, now choke coil will definitely it will oppose, it will actually exert some it will actually develop some impedance or resistance across the path. And whenever we are placing this iron core inside this choke coil, definitely the impedance that is offered by this circuit, it will be more. It means I can say overall heat loss will be more, and you will find this lamp is to be seen brightly but with a dim light. Clear? It means I can say intensity of this light decreases. Clear? So this will happen with part number D. Clear? Now if we are going to discuss part number E, why is choke coil needed in the use of fluorescent tube with AC mains? Why can we not use an ordinary resistor instead of choke coil? Now listen carefully. Actually, whenever we have supply AC mains, at that time VRMS that is coming to us, this is 220 volt. Clear? Let's suppose we do not have choke coil, we have only resistor. At that time this potential difference is very large, and at that time I can say, and instantaneously a large current will flow through this fluorescent tube, and this due to this large current we can say this fluorescent tube, it may be broken or it may be damaged. Clear? But let's suppose if we are connecting this choke coil, clear? So at the time some impedance is actually across this choke coil we will find, and there is some current is to be flowing, in a fluorescent tube. Clear? So that's why we can say we are using choke coil instead of choke coil with the AC supply. Clear? But if we have a DC supply, yes or no, whenever we are using choke coil, clear, we are not using ordinary resistor. Why? Because in the ordinary resistor, if you connect it, you will find that a large amount of heat is generated, because P equal to I square R. Clear? I square RT is the amount of heat generated. So large amount of heat generated, when large amount of heat generated, at the time definitely the circuit may be burnt. Clear? Or we can say this fluorescent tube, it may be damaged. Clear? So this is all about this question number E. Clear? So this is all about total questions. Now student, we are going to discuss this question number 7.23. Clear? In this question it is given to you a power transmission line feeds input power at 2300 volt to a step down transformer with its primary winding having 4000 turns. Okay, what should be the number of turns in the secondary in order to get output power at 230 volt? Clear? So now you can say a power transmission line feeds power at this one. So actually in case of a transformer, you know that EMF that is induced, it is directly proportional to number of turns. Clear? So from here you can say E2 divided by E1, this should be given by N2 by N1. Clear? Now you can say it is given to you a power transmission line feeds input power. So we can say output power we have 230 volt, input power we have 2300. Clear? Number of turns. Clear? In primary winding we have number of turns, this is 4000. So I can say this is 4000 and this is divided by N2. Clear? So from here you can say this is cancelled out, I can say 10. So value of N2 we are getting, this is 400. Clear? So now I can say number of turns we are getting, this is equal to 400. Clear to everyone? So now we can say this is all about number of turns. So this is all about this question. Now we are going to discuss question number 7.24. Clear? And in this question it is given to you, at a hydroelectric power plant the water pressure head is at a height of 300 meter and the water flow available is 100 meter cube per second. If the turbine generator has an efficiency of 60%, estimate the electric power available from the plant. Clear? So what are the parameters is given to you? Pressure head means we can say value of H, it is given to you 300 meter. Clear to everyone? Water flow available, it means we can say Q means rate of flow of water, I can say it will represented in meter cube per second, and this value is given to you 100 meter cube per second. Clear to you? Now turbine generator efficiency is given to you, this is 60%. Now we have to find the electric power available from plant. Clear? So I can say power is given by work done per unit time. Clear? Electric power available, power equal to work done per unit time. Work done we can write like this, this is force into displacement. Clear? Force into displacement, and we can say this is divided by time. Clear? So now we can say this is what we can say, distance upon time, this is equal to velocity. Clear? So power is given by force into velocity. Clear? Force into velocity. Now we can say this is power is given by force we can say this is pressure into area. Yes or no? Pressure into area. And I can say this is velocity. Clear? So now we can also write like this, pressure is given by rho gh, this is equal to A, and we can say this is velocity multiplied with velocity. Because jet turbine efficiency we have 60%, so I can see power output. Clear? Power output is given by 60 by 100. What about density of water? This is equal to 10 to the power 3. What about G? I am taking this is 9.8 because it is given in this question. Now what is value of A and H? Clear? So actually you can say value of H is already given to you, 300 meter. Now listen very carefully, what you understand by area multiply velocity. Area multiply velocity is actually, you can say this is equal to Q. Clear? How can we say? It is given by volume per unit time. Yes or no? Volume per second. Volume you can say this is area multiply distance upon time, and this is equal to area into velocity. So directly you can say area into velocity, this is equal to Q. Clear? So I can say this is equal to multiplied with Q. Clear? Now you have to just do some calculation. We can write like this, 60 multiply 10 multiply we can say 98 by 10 multiply we can say 300 multiply. What about value of Q? Value of Q we have, this is 100. Clear? So I can say this one and this one is cancelled out. Clear? And this value should be equal to, I can say this is 6 multiply 3 into 10 to the power 3. Clear? And we can say 6 multiply 3 we can say 10 to the power 3 multiply 98 multiply 100. Clear? Now if you solve it, you can find output power. Clear? So output power, I am just writing here, this is power output. Clear? Power output is given by 18 multiply 98. Clear? So we can write like this, 18 multiply 100 minus 2. Clear? Yes or no? So 18 multiply 98 and multiply 10 to the power 5. Clear? This value you are getting in watt. Clear? So from here you can say, we can write like this, 1800 minus 36. Clear? And it is multiplied with 10 to the power 5 watt. Clear? So now 1800 minus 36, this is equal to 1764 into 10 to the power 5 watt. Or you can also write it like this, 176.4 multiply we can say 10 to the power 6 watt. Clear? So this output power, it is given by 176.4 and this is equal to megawatt. Clear? So power output is given by 176.4 megawatt. Clear? So this is all about this question. Clear to everyone? Now student, we are going to discuss question number 7.25. Clear? In this question it is given to you, a small town with a demand of 800 kilowatt of electric power at 220 volt is situated 15 km away from an electric plant generating power at 440 volt. Okay, so much information is given to you. Let us try to understand, concentrate here. So let's suppose I am saying this is output station. Clear? Output station, and we have a small town. Here we have demand 800 kilowatt. Clear? We have this much of demand of electric power at 220 volt. Okay, and it is situated at 15 km away from an electric plant generated power at 440 volt. So let's suppose here we have electric plant and this is generating power at 440 volt. Okay, the resistance of two wire line carrying power is 0.5 ohm per kilometer. So let's suppose this is two lines and these two lines are carrying this voltage, or we can say this power from this end to this end. Clear? I can say this is source, this is power station, and we can say this is this is small town. Clear? This is town. Clear? Now it is given this distance between this town and this source, this is 15 kilometer. Clear? Resistance value is also given, this is 0.5 ohm per kilometer. Fine. The town gets power from the line through a 4220 volt step down transformer. It means I can say if we have, this is secondary side, at this secondary side we have voltage 220 volt, and this side we have voltage, this is 4000 volt. Clear? It is given in this question. Now we have to estimate the line power loss in the form of heat. Clear? First of all, can we calculate total resistance offered by this line? Yes. First of all, I am solving part number A. So I can say total resistance offered by wire. Clear? Now you can say actually we have two lines, that's why we can say 15 and 15. Total we have 15 kilometer, and this one is also 15 kilometer. So we can say total we have distance 30 kilometer. Clear? And one more thing is given to you, resistance is given 0.5 ohm per kilometer. It means I can say this is ohm per kilometer. So from here we can say kilometer cancelled out. And what about total resistance? Total resistance offered, this is equal to 15 ohm. So student, total resistance offered by wire, now we know this is 15 ohm. Clear? Now our objective is to find what is the power loss in the form of heat. Clear? So power loss we have to find. Now you can say what is output power that we needed? This is 800 kilowatt. Clear? It means I can say that is current flowing. Can we find in this situation? Yes. So we can find IRMS. Clear? I can write like this, IRMS. This is given by power output. Clear? And we can say this is voltage. So power output we have 800 kilowatt. So we can write like this is 800 multiply 10 to the power 3 and divided by, now we are getting this voltage, that is 400 volt, 4000 volt. Clear? So from here you can say this one and this one cancel out, we are getting this current IRMS, this is 200 ampere. Clear? So now can we calculate total power loss or total power loss when this current is going through this side to this side? Yes. So we can say, we can write like this, power loss. Clear? It is given by IRMS whole square multiplied with R. Clear? Now what is value of IRMS? IRMS value we have, this is 200 square and multiplied with R. Clear? R value is given to you. Yes, you have calculated, this is 15. Clear? So this is multiplied with 15. So from here you can see we are getting this is 400 into we can say this is 100. Yes or no? 400 multiply 100 and we can say this is 15. So from here you can say this is 600 into 10 to the power 3 watt. Yes or no? So now we can write like this, this power loss we are getting, this is 600 kilowatt. Clear? So this is answer of your part number A. Clear? Total power loss in the form of heat we are getting 600 kilowatt. Clear? Second, how much power must the plant supply assuming there is a negligible power loss due to leakage? Clear? How much power must the plant supply? Now listen carefully. What is total demand of power? 800 kilowatt. What are the amount of power loss is to be taking place while carrying from one end to another end? 600 kilowatt. So total power that must be supplied by the plant, it should be. Now we can see total power supplied by plant. Total power supplied by plant, and it is given by we can see total power supplied by plant. Clear? This is equal to, we can see first 600 kilowatt, this is power loss due to carrying from one end to another end, and 800 kilowatt we have in demand. So directly you can say 1400 kilowatt. 1400 kilowatt, this much of power is to be supplied by plant. Clear? So now I can say we are having answer of A and B. Clear? Now what about C? Characterize the step up transformer at the plant. Now you can see at this side we have 440 volt and in this side we have, this is 4000 volt, clear. So how can we find this voltage, clear? How can we calculate? So actually, can we find what is voltage drop? Can we find what is voltage drop at this line? Yes, yes, we can calculate. So voltage drop we can calculate. This is given by IR. Value of IRMS we have, this is 200 ampere. What about, we can say resistance, this is 15. So we are getting this is 3000 volt, clear, 3000 volt. Now you can say already we are having this side, this is 4000 volt, clear, and we can say there is a loss of potential that we are getting due to this resistance, and that is equal to of 3000 volt. So I can say V input, or we can say voltage that is available at the secondary coil this side, it should be equal to 4000 voltage. This is required for the secondary coil, and 3000 that is lost due to resistance, clear. It means I can say it should have 700 volt, clear. It means I can say if I am talking about step up transformer, it should have 440 and 7000 volt, clear. 440 and 7000 volt, we can say that is input is required, clear. So this is a rating of step up transformer, clear. So this is all about part number C, clear, and this is all about this question. Now student, we are going to solve this question number 7.26, clear. In this question it is given to you, do the same exercise as above with the replacement of the earlier transformer by 40,000 and 220 volt. Okay, step down transformer. Now concentrate. Let's suppose if we consider situation of a previous question. Actually we need output power, this is 400 kilowatt, clear, and it should be available at 220 volt, clear to you. But there is one change is to be taking place. Yes, definitely this line is having again resistance, and resistance value is given to you 0.5 ohm per meter, clear. This distance is given 15 kilometer, clear, and this side we have this power plant, or we can say this is generating power at 440 volt, clear. So now only one change is to be taking place in this question. Instead of 4000 volt, now we are saying this is 40,000 volt, clear. Now we have to find which one is good, is high voltage transmission is preferred, why, clear. So now let us try to understand. First of all, can we find total current this is flowing? Yes, we can write like this, IRMS. It is given by, we can say power output we have 800 multiplied 10 to the power 3, and what about potential? Potential is given 40,000. So I can say this is 40,000. 1, 2, 3, 1, 2, and we can say 3. So this one is 3. So this is 100, and this one is cancelled out, clear. So we can say IRMS we are getting this is 20 ampere, clear, because we have potential difference 40,000 volt, we are getting only current, this is 20 ampere, clear. What about resistance of this wire, or we can say what is the resistance between these two locations, clear. So resistance offered it is given by, and we can say 0.5 ohm per meter multiplied with total distance we can say 15 and 15 total 30. So again you are getting this value 15 ohm, clear to everyone. This is 15 ohm. So we can say this is value of R we have, okay, fine. So this is value of R, and now we have to find this is IRMS and we are getting R. So can we find power loss in this transmission? Yes, we can say this is given by IRMS square multiplied with R, clear. What is value of IRMS? IRMS is given to you 20. So we can say this is 20 square multiplied with R, clear. Value of R we have, this is 15 ohm. So we can say this is equal to 400, clear. 400 multiply 15. So we can say 60, and we can say this is 6000 watt, clear. Or you can say this is equal to 6 kilowatt, clear. It means if we are sending this power, or we can say this current at 40,000 volt, at the time there is only loss of 4 kilowatt is to be taking place in this transmission, clear. So it means I can say what is the power, total power it is to be given at this level, clear. So I can say if you are talking about total power, clear. So power it is given by 800 kilowatt that we have to supply to small town, and 6 kilowatt power we are getting. So this is 806 kilowatt. Clear to you? Now let's suppose if we want to know, let's suppose definitely for that one we are using step up transformer. So what is rating of that step up transformer? So we can see how can we calculate here total potential drop? Yes, we can write like this. Potential drop is given by IRMS multiplied with R. Clear? IRMS we have, this is 20 ampere, and what about resistance? Resistance is given to you 15 ohm. So we can say this is 15. So we are getting this is 300 volt. Clear? So now we can say 40,000 volt we are getting at this coil. Clear? At this end. So definitely if we talking about this transformer, it should have 40,000 plus 300 volt, because 300 volt potential drop we are actually losing due to this resistance. Clear? So now I can see what is the rating of step up transformer. Clear? For step up transformer we are getting this rating, this is equal to, I can say 440 volt, and from there 4300 volt. Yes or no? Clear to everyone? Yes. So can we find what is the total percentage loss? Clear? So I can see if I find percentage loss in first situation or in the previous question. Clear? You can say at the time you are saying 600 kilowatt is lost and 400 kilowatt you are giving you are taken from this power plant. Clear? So from here you can say this one is cancelled out, and this is equal to 600 divided by 14, and we can see if you multiply, if you divide it, you can see near about 43% loss you are getting. Clear to you? But what will happen whenever we are talking about percentage loss in this question, in this particular question, you can say only 6 kilowatt power we are losing, and we are giving input as 608 kilowatt power multiplied with 100. Clear? So now we can write like this, this should be equal to 600 divided by 806. Clear? We are saying this is 806, and we can see this should be equal to, now 600 divided by 806 means this is less than 1. Yes or no? It means we are getting this percentage 0.74%. Now you can compare in this question. In this particular question you are saying that only 0.74% of the total power given is going to the waste. Clear? It is result in a wastage. Clear? But in the first situation 43% of the power is wasted. It means now we can say yes, it is always be better if we are giving power at a higher voltage. So higher voltage transmission is always preferred if we want to reduce the power loss. Clear? So this is all about this question. So dear student, this is all about NCERT discussion, class 12th, chapter number 7, alternating current. Clear? So hope you enjoyed this session, and definitely these solutions will be very useful to you, as well as you will find the exact video solution of each and every question. Clear? And definitely you will be benefited in your upcoming examination. Clear? So revise all these questions again and again, and good luck for your examinations. Thank you so much.